So the first thing we're going to look at this time is constructing finite difference approximations using Matlab. Finite difference approximations approximate derivatives of functions. So one thing we could do is take a look at a certain function, maybe a polynomial, for example, like this. Okay. And yes, it's true that we could certainly define a value of h, and just at one point, let's say x naught equal to 1, I could evaluate my function. And let's see, let's put some parentheses around this. And this is the numerator of a divided difference, where I divide by h. And that'll be a good approximation, not a great one, but a good one, of the derivative of f at x naught equal to 1. But what we'd like to do is go a little bit further than this and construct let's say over an interval t, where we can plot f of t. Okay, there's the function, the cubic function I've defined. Can I now also look at f prime? And I don't want to compute f prime using calculus. I'd like to do it with my finite difference approximation. Okay, so how could we do such a thing? Well, the key to this is getting an automated formula so that I could, for each value of t that's stored, there's 2001 of them from -1 to 1 at the moment, each one of those I'd like to store an approximation to f that looks like f prime and is built by these finite difference approximations. Okay. So to that end, what I've got here is this function. Okay. Fp comma x is the finite difference first, that's the first order derivative, of f over the interval from a to b with n subintervals, or step sizes of equal spacing. And here is, in the documentation of this Matlab script, here's how we use it. Okay, so for example, let me one by one copy and paste these lines. Let me clear the command window. Okay, and now I can copy, I can paste. Okay, so now we've got a function. Continue on like this. And maybe it'll be a little faster just to type it in, I guess, but I'm just replicating what's in the usage. Okay, so this is going to go from 0 to 4 with 100 steps. We're going to compute f prime, that's fp, and let's store the x values from 0 to 4. Finite diff. And the syntax is exactly the same. Note above that I have defined f, a, b, and n. So all my inputs are available. I run the code. And what have I done? I've not changed my current folder. So let's do that. There we go. Okay, so this ran the code, and now notice the last command. I can run that now. Let's plot x versus fp. Okay. And what this is that we're looking at is the derivative of the cosine of x squared. In fact, what we could also do is let's plot the analytic derivative of the cosine of x squared. For those of you keeping up by pen and paper, please feel free to replicate my computation here. But I'm just getting this from applying calculus. Okay, so the derivative of cosine of x squared uses the chain rule. So we've got -2x times the sine of x squared. And here, let's put this in as a dotted red line against the blue line, which is the finite difference approximation. And as you can see on the graph, we've got a blue line and a red dotted line basically overlaying it perfectly. In fact, if I were to, let's switch over to the figure tools. Whoops, let's try a zoom. And if you get somewhere around this peak, for example, we can see there are in fact two different curves here. Okay, the red dotted line is again the exact solution, and the blue is the approximation due to the finite differences. Okay. If we look at the documentation of this program, a little bigger here. Okay. It says that it is a second order accurate finite difference approximation. And what that means is that if h is small, let's say 0.1 or 0.01, the error will be around 0.01 squared, 0.1 or 0.01 squared. Okay. If you do take a look into this code, there's some things to notice. There's not many lines of this code. FP1 is a little tricky to compute because we have to use what is called a one-sided finite difference stencil. Okay, this is something we didn't see in the typical course. Here is the Matlab version in this for loop for computing the second order accurate central finite difference formulas. So notice that f prime at the kth position is based on f of x at k plus 1 and k minus 1 and divided by 2h. So that's the central finite difference approximation. But these first and final points, the derivative is approximated using a one-sided stencil that is second order accurate. So these are a little bit more complicated than the forward and backward difference formulas that we learned in class, but it's the same idea. Okay, and so that gives us the ability to plot an approximation of f prime. Well, once we have the first order understood, I can use in my workspace, I still have all the same information. Let's compute f double prime. So let me just copy over the syntax. Note that we're still in the right folder. This is where the file is, so I can paste into the command window. Okay, and now I can start to plot x versus f prime and f double prime. And again, let me put a different line indicator here. Let's make it a dash dot line that's black. Okay, and there we are, looking at f prime and f double prime. And there's one more file available. We can do this with the third derivative as well. And then we'll be able to plot all three of these on the same set of axes. So let me have PL, and I can go up in my command window, hit the up arrow on the keyboard, and I can autofill the previous command. And the way I'm going to do this is just sort of copy and paste and bring f double prime into f triple prime. And maybe I'll make this my dashed red line. And that's all three of these plots of f prime, f double prime, and f triple prime on the same axes. And then the last thing I can do is I can start to copy over some of this history into my assignment template. And let's see here. I'm going to have to make some adjustments, but let's plot the finite difference approximations of f prime, f double prime, and f triple prime on the same axes. Okay, and let's go back and get the history of what I've written from my command window. So I can hit the up arrow, and let's see how far back. Well, f was important. A was important, and B was important, and what else did we say? That N should be around, what did I have? 200, I suppose. No, 100. Okay. And then we're just going to have a few of these now. I can just replicate these. Okay. Because the syntax sort of matches once we get the idea of things. F double prime, this is F triple prime. So we can compute the first derivative, the second derivative, and then the third derivative. And that's coming from these downloadable Matlab scripts, which are basically the same except for what's done in the for loops. Notice here in second finite difference, for example, x of k plus 1, x of k minus 1, and we're dividing by h squared instead of dividing by 2h. So this is the second order finite difference approximation of a second derivative. And finally we'll have a second order approximation for the third derivative here. And notice for finite difference third, getting a little bit more complicated, and this is due to what's called stencil runoff, meaning that because this third derivative requires 4 points of f, I'm going to have more points, namely the first and the second, where I have to modify my stencil. Okay, and these are things we didn't cover in the lecture, so I'm not expecting you to know these, but I'd like you to at least be able to run these files. And so finally, if I go back to my assignment template, Okay, I've got fp, f double prime, and f triple prime set up for this particular function over this interval with this number of points, and I'm going to plot them all. So if I run this, okay, there's my plot, but now it's in the .mlx file and I can look at it live. One last thing I should point out is, notice how there's some sort of not an error message, but a warning message coming from Matlab. It looks as though there's multiple definitions of x. Okay, and so what we want to do here, what we can do, is just ask for the first input only, because there's already one copy of x coming from the first function call. Okay, so the first finite difference will produce f prime and x. The next ones I can ask just for FDP and just for FTP, double prime and triple prime, respectively. Okay, and so that's how we can use Matlab to construct finite differences and then use and then plot those, on one graph.